let's do a quick little overview, okay? So overview of the course, even though we're not done yet. What are like the 4 courses of high school? Yeah, pre-algebra, algebra. Yep. Algebra, geometry, pre-calc, yes, yes, and trig. Okay. So these are like the big 4 things that you learn in high school if you end up taking calculus at the end of high school, right? The like BC Calc or AB Calc route is you in some order, you take algebra, geometry, trigonometry, then you're ready for pre-calculus to calculus, some version of that. And what I really want to do with this course is explain why. Why these subjects? What like how did this come together that these are the things that people are interested in? We've spent a lot of time talking about geometry. And I want to make sure with 3 lectures left, so geometry, I'll say we're done talking about geometry. With 3 lectures left, I want to explain why these 3 are there. Calculus probably, I'll give a vignette in calculus. We've already talked a little bit about calculus in Newton. By the way, did you guys watch the various videos? Let's see, where's that course website? Here it is. So hopefully you guys are clicking on these things and reading the various, there's a video that finishes our discussion from last time about Newton's computation of pi. We talked about Pascal's triangle and Newton's binomial theorem, but we didn't take it all the way. So hopefully you're clicking on these various links and checking them out and exploring them and learning about what's there. It's like extra resources for you. Okay. So we'll talk about algebra. We'll talk about trig. So today I want to talk about trig. So what happened? Why did trig become an important subject? And what is trig? Okay, historically. And for that, this is a little presentation I've given to the public before, so let's see if it works here. So this is one more time. We're still in the ancient Greeks, I think, for one more lecture. And this is about the ancient Greeks measuring the heavens. So they would see the night sky. Let's talk about that in just a second. Trig, what do you think of as trig? We were just talking about high school. In trig, it's SOHCAHTOA, it's opposite over adjacent, and sines and cosines, and like just the subject is a mess. And it's very easy to explain why algebra is something beautiful. Well, hopefully you'll agree with me. And calculus and geometry, these are all things. Trigonometry is one that for some reason, like I felt the need to write this is my approximation to a love letter to trigonometry, okay? Why you should appreciate trigonometry. So for about 300,000 years, this is not what nighttime looked like, okay? 150 years ago, we got artificial light. And pretty soon thereafter, this is what you see at night. What every single human being that has ever existed, modulo the last 150 years, except for us, saw every single night was this. You get into your tent, your teepee, wherever, whatever kind of shack you live in. Nobody had, the kinds of housing that we have today. And you would lie there. Hopefully you can see this. You would lie there at night, and all night, every night, you would see these stars, and you would get to know these stars, and they'd be your friends, and you would say, hey, I know that one. And really what's going on is as the night progresses, this is sped, I found this YouTube, somebody sped this up. As the night progresses, this thing moves. Okay, there's some clouds. But there's something very interesting that as the night sky is moving, if you open the camera filter, you'll notice that most of the stars are moving, but one of them is not. Anybody know which one? Polaris, exactly. So if you watch it again, Polaris is right there. That's the northern, that's the star. It just so happens, this is not true in the southern hemisphere. In the northern hemisphere, it just so happens that there is a star in the direction of our axis of rotation around ourselves. So that's Polaris, the northern star. So this is what people got to know, and they got to know the fact that the stars change during the seasons, right? We would have different patterns of stars in different seasons. These are the, what are they called? Not The constellations, thank you very much. I'm thinking of astronomy, not astronomy, astrology. Astrology is, oh, Mars is in retrograde and therefore you should not get married or something, right? It's this kind of nonsense, abject nonsense. Polaris is there. So people were like, they would see these constellations. They would observe that they happen throughout the seasons, and they would also see that some of the stars in heaven were moving against the other fixed stars, and those stars became known as planets. Planets. They didn't know what planets were. They just saw that there were these other things that like moved. All the other stars stayed together as one celestial sphere, and then there were these other stars that for some reason moved across. They're ones that are visible with the naked eye. By the way, when we talked about the Platonic solids, I forget who mentioned after class, the Kepler had this beautiful model of each solid inside the others nested in a way that was similar to the 5 known planets at the time, that their orbits there's some similarity between the relationship between going from a tetrahedron to an octahedron to a cube to an icosahedron to a dodecahedron that resembles Mercury to Venus to Earth to Mars to Saturn or something. Okay, so people are looking up at the night sky. What every single civilization period has discovered is that there's about a 365-day cycle of, if you just start keeping track of tabs and then it snows all of a sudden, or it becomes rainy and it becomes hot, becomes cold, you notice these things. And so you keep tabs for days long enough, you'll notice that 365 days you're getting this cycle of weather. So everybody observed that. Of course, we have the moon. A month is 29 days, and it goes through these phases. So what are the phases of the moon? Have you guys ever thought about this? What's happening when the moon? We don't think about the moon, by the way. We'll get to calendars in just a second, but a month is really a month. It's meant to have something related to, that's why it's about 30 days. What's that? No, nothing. I thought I heard something. A month, yeah, call it a month. You absolutely should. So here's what we today understand is that the sun is at the center, gravitational center of our solar system. The Earth and all the other planets are going around that. The moon is going around us. So, but the angle, the ecliptic is the plane in which the Earth moves, and then there's a different plane at which the moon moves around us, slightly different, 12-degree angle. And so that's why when the moon is sort of between the sun and the Earth, but not most of the time, it's not blocking the sun because it's off by this angle. And the moon is relatively small, although the moon and the sun, we'll talk about this in a second, look the same in the sky. They're about the same size. This is an amazing accident of the universe that this just happens to be the case on our planet. And we'll talk about that more too. So when the moon is here, like the sun is always hitting the moon and lighting up half of the moon. But when the sun is there and the moon is here, what do we see the moon being lit up as? Nothing. We're seeing the dark side of the moon, right? So if you're looking in the daytime, the sun is very bright, the moon is close to being in front of the sun, and none of it is being illuminated, you don't see a moon at all. Okay, so that's a new moon. Then the sun's still there, the moon comes over here, and now what will I see? Half a moon. I'll see exactly half a moon. Then the moon comes back here. Now, sometimes the moon is blocked by the Earth, and so you get lunar eclipse, but most of the time it's not because it's moving on this other axis. So what do you see? A full moon, then back here, half moon, and over here, a new moon. Okay, by the way, in those 30 days, the Earth has also moved. So there's some very subtle things happening about, I shouldn't be drawing this picture standing still, pointing to the sun over there. The Earth is also moving while the moon is moving. But because this is about 28 days, some can hypothesize that the number of days to go from a new moon to a half moon is about 14 would take you halfway around. A week. So we could be the, if there's a new moon on Monday, there's going to be a half moon the following Monday, and there's going to be a full moon the following Monday, and another half moon the following Monday, and finally a new moon the Monday after that. Of course, that's not quite right. We have now, for whatever reason, standardized 7 days exactly, regardless of the moon, of what's happening to the moon. Whereas the moon, again, is about 29 days, especially given our extra motion here. So people figured this out. Like, these are the kinds of things that you just can't help, humans can't help but find these kinds of patterns. Okay, so like nearly every civilization figured this out. By the way, this raises an interesting question. How should you make a calendar? How should you keep track of time? You could either track just making sure that we go around the sun and track the 365.25 days, or you could keep track of the positions of the moon, or you could try to somehow to keep track of both the positions of the moon and the position in the sun. Curiously, half of the world, about 4 billion out of the 8 billion people on this planet, follow an Abrahamic religion, at least culturally, and the big three there being Judaism, Christianity, and Islam. And in each of these three traditions, just by happenstance, each one chose a unique one of the three possibilities. So the Christian calendar, the one that we're following, the reason it's called AD, the year of our Lord, it's not because the country has Christianity as an official religion or something. I mean, it's not about the country, it's about the entire Western world. It's that this was the calendar. What is this calendar called? We've talked about this before, I think. The Gregorian calendar. Okay, so Pope Gregor assigned people. The calendar started getting off from the seasons. And so in the anybody remember 1760s? Late 1700s, at some point there was a recalibration to make sure that the solstice is happening when it's supposed to, when we're actually pointing in one direction or another relative to the sun. So the West follows the Christian calendar, and the reason you say month and not month is because months have nothing to do with moons. Okay, we just said this month is 30 days, this month is 31 days, this month is 28, sometimes 29. That's because there's 365.25 days in exactly one full revolution of the Earth around the sun, and that's it. So the Christian calendar is purely solar calendar. Who cares what's happening with the moon? Not who cares, but when we start a new month has nothing to do with when there's a new moon. The Islamic calendar is solely a lunar calendar. So it just follows, there are 12 months in the year, and those 12 months continue following exactly when every time there's a new moon, there's a new month. And so the holy month of Ramadan, for example, will move throughout the year over the cycles, because there's really some years there's 12, some years there's 13. So it's designed so that the months, the festivals that are celebrating historic events change throughout the calendar. So there'll be things from the spring that are happening in the winter, and then 10 years later it's happening in the fall, and so on. And the Jewish calendar is a solar lunar calendar, which every single time there's a new moon, there is a new month, but instead of having leap days to make sure that they're staying with also the precession of the sun, they have leap months. So maybe you noticed, by the way, this year Easter was particularly late, right? It was like end of April. You guys remember, like Easter break was like, yeah, who knows? That was last semester. Yeah, that was so long ago. That's because this year there was a leap month, and Easter is tracking Passover because the final supper was a Passover Seder, and so that got pushed back by a month, and so Easter got pushed back. So anyway, there's all this like really, really interesting stuff about keeping calendars. Very interesting mathematics there. We're not going to talk about it at all. It's just curious that there are three possible choices you could make for how to keep calendars, and the answer for which one should you choose is yes. Okay, all three were chosen, and these are all major decisions that were chosen. Okay, so of course the modern interpretation of what we're seeing in the pictures of the planets going and the stars going around us is that the stars are fixed and we're the ones that are moving, right? It's we are rotating. This is the Earth rotating about its axis at night, keeping the stars fixed. And so what most textbooks, and I even hear physics professors say, Copernicus was the one who in the 16th century suggested heliocentrism as opposed to geocentrism, meaning helio is that the sun is at the center of the universe and not the Earth. And then we learned about people like Galileo and Kepler, Brahe, Newton, Hubble, all of these great names in the Renaissance, in the modern era. And that's where we get heliocentrism from, right? Wrong. We get it from trigonometry and from the ancients and with no tools. So let me try to explain. So today we have all this fancy equipment. We have rockets, we have satellites, we have spaceships that go to the sun, and we go to the farthest reaches of our solar system. From these, we're able to compute that the circumference of the Earth is about 25,000 miles. The diameter of the Earth is about 8,000 miles. The moon is about a quarter the size of the Earth. The sun is about 100 times the Earth. And the distance to the moon is like 250,000 miles. And the distance to the sun is 100 million miles. So the distance to the sun is 400 times the distance to the moon. And the size of the sun is also 400 times the size of the moon. Okay? There's no way we could possibly compute these things without all of our modern equipment and technology. What do you think? Wrong. This was all known to the ancients. And the person responsible for this is named Aristarchus. So Aristarchus is slightly older than Archimedes. And there's another guy that we're going to talk about named Eratosthenes, who is slightly younger than Archimedes. So we're sort of straddling Archimedes. They're right around, and they were all somewhat contemporaries. They're like, one is 10 years older than another, and another is 20 years older than the last. So he's in this island of Samos. I don't know how well you can see that. Yeah, some Greek island. And he showcases the power of trigonometry. So trigonometry literally means trigon, triangle, metry, measuring things with triangles. But it has a much deeper meaning to me, which is measuring things you can't touch. No one has run a ruler to the moon. We're not going to put a ruler around the sun and measure its circumference or diameter. And yet we know these things. How? How is that possible? Trigonometry is how. So using only his mind and extremely clever ideas and very basic observations, he computed almost all of the things that we discussed. And then Eratosthenes will finish off the calculation that will allow us to compute every number that we just mentioned, is a number that you can learn from first principles. Okay, so going back to, I forget when we were having a discussion about the flat earthers, the ancient Greeks could figure this out. The flat earthers could figure this out too. So let me explain to you how he does it. So far, so good? Okay, so step right up, we're going to measure all these things in 4 easy steps. So step 1 is we want to compute the relative, bless you, the diameter, the relation between the diameter and the distance to the moon. So how could you do that? You wait for a full moon. That happens once a month, roughly. And you take a dime, which has diameter, I'm told, 0.7 inches, and you tape it to your window where you can see the moon. And then you just step back until the dime perfectly covers up the moon. Okay, until you have this situation where from your eye, the dime is just perfectly covering up the moon. What can you learn from these similar triangles? If you know the ratio of the dime's diameter to the distance to the dime, that's the same as the ratio of the moon's diameter to the distance to the moon. Everybody see that? That similar triangle? So the dime's diameter, I already told you, 0.7 inches. If you, bless you, run out this experiment and run a ruler to the window from your eye, you'll see it's about 90 inches. You have to stand about 90 inches away from the window for the dime to perfectly cover up the moon in the night sky. Okay? And if you divide 0.7 by 90, you get 8 1/1000ths. very roughly. So we just learned something very interesting. We did nearly nothing, right? Okay, we didn't actually do this experiment, but you can believe me that we could do this experiment. We did nearly nothing, and we have learned that the diameter of the moon relative to the distance to the moon is 8 to 1,000, 8 1,000ths. Okay. We've actually learned two pieces of information. Did anyone go to see the total solar eclipse in April? These are two things in April. That Easter was late, and we had this incredible eclipse. You had to drive to Vermont or something else nearby to see it. So I took my kids, and it's totally crazy. You're just standing in the woods and minding your business. Like I'm imagining 3,000 years ago, you got your goat herder or something. You're just, minding your business. You're not there for the eclipse. You don't even know the eclipse is coming. And all of a sudden, God turns off the lights. You're like, holy crap, what just happened? And you look up at the sky where the sun used to be, and what you see is this black angry eye staring down at you, and you're like, what sin have I committed to cause this? Like, quick, sacrifice a virgin or something. Like, what are we going to do to get the lights back on? 3 minutes later, whoosh, lights come back on. And you're like, okay, got to remember whatever it is that we did just now, whatever prayer, whatever sacrifice, like do that again if that ever happens. We really screwed up here. Like, could it be that the reason we have intelligent life on Earth, like maybe life is possible, but intelligent life is because there just so happens to be a moon, which is exactly the same size, at least in the sky, as the nearby star? I don't know. That question is above my pay grade. But like the fact that this phenomenon exists is just astounding. Like we shouldn't just be looking for Goldilocks planets in faraway galaxies, but Goldilocks planets with a Goldilocks moon, where this kind of phenomenon can cause someone to start thinking about, things that are way above their own pay grade. Like now you're forced to deal with the heavens. God's mad at you, right? Okay, anyway. So people know that total solar eclipses occur. In the total solar eclipse, the moon is completely blocking out the sun. So again, it's the same thing as the dime to the moon is happening with the moon and the sun. The moon is perfectly blocking out the sun. And so the ratio of the diameter to the sun to the distance to the sun is the same as that of the moon and that of the dime. It's this 8 1,000ths. Does that make sense? So again, we need to have experienced things like total solar eclipses, or at least have read about them, have heard about them, and do this one experiment. And so far we have those two pieces of information. So far, so good. Yes, total solar eclipses were, the prediction of eclipses is something the Babylonians worried a lot about. The Egyptians, the Egyptians, their main god is the sun god, right? So when this kind of stuff happens, it's a big deal. And so, I believe they did. They thought it was definitely connected to big problems in something they were doing with their lives. They're like, we got to get straight and narrow, fix what we're doing. Yeah. 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 Layla, you want to say something?
Well, it's more of a question.
Yeah.
With this dime experiment, was it actually done like with a dime, or did they use some other, is this just like a modern placeholder?
What I'm doing with this, these are all thought experiments, and I'm sort of imagining how would I today reconstruct all of these experiments and from first principles work out these values, of course being guided by the genius of Aristarchus that you have to look for these things. You don't need a dime. You don't need a window. Maybe you have a friend hold up something that you can measure. The point is, I can measure a dime, and I can measure the distance to a dime. And now I'm going to infer from that things that I have no chance of measuring, like the diameter of, well, I haven't measured the diameter, but I've measured the ratio. What trigonometry allows, trigonometry is about similar triangles. So I can measure the ratio of the distance to the moon, to the diameter of the moon, and same thing with the sun, just from doing a local calculation that I can do with a ruler. Okay, does that make sense? So this is the amazing thing about trigonometry is measuring things you can't touch. I can touch a dime. I can measure the dime. I can't touch the moon. Okay, let me record these things just so we have them here. So diameter of the moon to the distance to the moon is the same as diameter of the sun to the distance to the sun, and is 0.008. That's what we got so far. All these numbers are extremely rough, of course. We're not being precise about anything. And the measurements will have rounding errors that are so large, we shouldn't treat any of this too seriously. But I just want to get the thought experiment is what's important here. Could we come up with this? Okay. So far, so good. Any questions? All right. So his next Aristarchus. So step one wasn't really Aristarchus. Step one is something anybody could have worked out, and people did, and the Mayans and the Babylonians and the Indians and Persians and Chinese had all of this information. Aristarchus says, wait a second. Remember we talked about this half moon? What is actually going on when you see a half moon? So this is a picture I took. You probably can't see, but the moon is right there, and the sun is right there. This is, I mean, it's being distorted because I took a panoramic picture. Let me zoom in on that moon. So hopefully you can see that that's about a half a moon. So that half a moon is over here, the sun's over there, and you can see both in the sky at the same time. And so what Aristarchus says is, what does it mean that you're seeing exactly a half a moon? There's always a triangle. There's always this triangle. There's always this triangle between the moon, the earth, and the sun. And if you're seeing exactly a half a moon, and you know when it's coming, because you just had a new moon, wait 7 days, 7 and 8 days or something, it's going to be right about here. What does it mean that we are seeing that half a moon? The triangle goes from a new moon, which is basically like a straight line, to over here, we get a right angle at the moon. Okay, so let me just draw this again here. So at a half moon, the reason we're seeing a half moon, so here's the sun, here's the moon. There's always a half moon. It's just a question of, there's always half of the moon that's being lit up. It's just a question of what do we see from Earth? Sometimes the Earth is over here and we don't see anything. Sometimes the Earth is over here and we see the full moon. And when we see a half moon, it's because the Earth is looking straight here, and the sun, of course, is always going straight to the moon. And so this must be a right angle. The moon must have a right angle. But standing on the Earth, we can measure this angle. And the question is, what is it? You're standing here on the surface of the Earth. You can point one finger to the moon and point one finger to the sun and see what that is. And so I'm imagining standing here, when I took this picture, I pointed one finger to the moon, one finger to the sun, and tried to figure out what that angle was. And this is exactly what Aristarchus did. And can you guess what angle? I mean, okay, it says there, so don't read what it says. Can you guess roughly the size of this angle? Is it going to be like 15 degrees or 30 degrees? Marley, you read the thing? It's very nearly 90 degrees. But that's a problem. What do you mean it's 90 degrees? That means, so again, here's the sun, here's the moon. We know that there's a 90-degree angle here. How can there be a nearly 90-degree angle here at the Earth? That means the sun is like infinitely far away. It's way, way, way farther away than anything else. Even though the moon is presumably super far away, we don't actually know, right? If you're just standing on Earth, like, how do you know the moon isn't just 20 feet off the ground? You can try to like build a ladder or a tower if we all speak the same language. We could build a tower and try to reach the moon. We know now that the moon really is very far away, but but whatever it is, what we definitely know is that the sun is very far away, And the sun is very far away, at least compared to the moon. And so the sun must be huge, at least compared to the moon. We know that they're the same size before we did this calculation, it might be that the moon and the sun are basically the same size and the same distance. They just don't happen to crash into each other, but that's why they line up. But now we know just the fact that this angle is large is that the sun is way, way far out relative to the moon. Now we can actually be more precise in that if you measure this angle, so remember that the diameter of the moon to the distance to the moon is this 0.008, the same with the sun. Of course, you don't put a dime and try to block out the sun, you'll block out your eyes. But that mystery angle, it turns out, is 89.86 degrees. And this is also very, very rough because it changes during the seasons and over time and so on. But roughly, we can think about that as like 89.9. It's almost 90. Aristarchus approximated it as 87. And you'll see that that's going to cause a serious problem. So what does that mean? If this angle here is 89 point, what did I say, 86 degrees? So in this triangle, what is the ratio of the distance? So here's the distance to the moon, and this is the distance to the sun. This is the distance to the sun. This side is the distance to the moon. So what is the ratio of the distance to the moon to the distance to the sun? Relative to this angle, we have adjacent over hypotenuse. Anybody remember what that is? Cosine. This is cosine. Cosine of 89.86 degrees. And so if you want to invert this and say, well, so what do we know about the distance? So the distance to the sun is equal to, let's see, if I multiply the distance to the sun this way and I divide by the distance to the, so cosine, if I divide by cosine, that's secant. So this is the distance to the moon times secant of 89.86 degrees, right? Secant is 1 over cosine. Remember that? And so the question is, what is secant of 89.86 degrees? Well, okay, let's remember what secant looks like. So cosine, Layla.
Secant to find the distance?
So we're finding the relative distance. We still don't know any of these numbers absolutely. We don't know it's this many miles. What we know is the proportion, however far away the moon is, the sun is much farther away. And the question is how much farther? We're always measuring distances from Earth. That's the only place we're here. The only thing we can think about is not the distance between the moon and the sun, but the distance from us to the moon, the distance from us. So we can measure from Earth to moon. We're trying to measure from Earth to moon. We're trying to measure from Earth to the sun. Okay, these are the distances: the distance to the moon, the distance to the sun. This distance, we're not on the moon. We're not on the sun. And it changes, of course, because the moon is, well, it doesn't change by much. Okay, so let's think about the secant function for a second. So what is the graph of cosine? Anybody remember what cosine looks like? Yeah, it's this kind of, right? It's like the sine curve like that. So this would be, well, let's finish the whole period. So where's this? If this is 0, this is 2 pi or 360 degrees. And so this would be pi. And so this would be pi over 2. Okay, so this is near 90 degrees. And so secant is 1 over cosine. Yeah, so secant is 1 over cosine. So at 1, it's 1. And then it has this vertical asymptote at pi over 2. And so secant's blowing up. And so you see the difference between 89.86 degrees and 87 degrees is massive. So Aristarchus had computed 87 degrees. I'll put it here. Aristarchus computed 87 degrees and got secant equal to 20. And the truth today, as we understand it today, is 89.86 degrees. And the secant of that is like 400. So remember that number 400. I said the distance to the moon is, the distance to the sun is 400 times the distance to the moon. That's what gives us this calculation. So this secant is around 400 in actuality. Does that make sense? Everybody see how we got that? So just from measuring this one angle at the half moon, we get another little piece of information, which is the relative distance to the sun versus the moon. Does that make sense? Okay. So yeah, so again, this calculation, as you see, a tiny variation in your measurement of the angle leads to a huge variation in that relative proportion because the secant function is blowing up near 90. Okay, does that make sense? All right. So let's recap. What do we know? By this, the dime and looking at our eye, we know that the distance to the moon relative to distance, the diameter of the moon rather, relative to the distance to the moon is 8/1000ths. We know the same holds for the sun because of solar eclipses. And what we just learned is that the distance to the sun is 400 times the distance to the moon. But again, because they have the same ratio, that means that the diameter of the sun is 400 times the diameter of the moon. Right? They're again in proportion. So the distance to the moon is 1/400th of the distance to the sun, but they look the same in the sky, which means that the diameter of the moon is 1/400th the diameter of the sun. So far, so good? Everybody with me? We still don't have enough information to solve for all of the unknowns, and this is where we get to step 3. This is still due to our Aristarchus. So for this, we have to talk about lunar eclipses, total lunar eclipses. We talked about solar eclipses. What's happening at a lunar eclipse? So here's the sun, here's the Earth, and here's the moon that's going around the Earth. At some point, remember there's this like 12-degree angle that the moon is off from the ecliptic of how we go around the sun. If it so happens that as we're crossing this plane, we also cross that plane, that's where we get a total lunar eclipse. Okay. So the first thing that happens is the moon, out here, the moon is being lit up completely by the sun. Then we enter what's called the penumbra, where some of the moon is no longer being lit up by all of the sun's rays, but it's still being lit up by some of the sun's rays. So it's not getting as much sun as it should, but it's not yet nearing totality. Okay. So even when you're here, the moon looks almost just as bright as it did here, merely because the sun is so damn bright. But then we start entering the umbra, and now we're getting to the point where, in theory, none of the sun's rays should be approaching the moon, so that when the moon comes back here, it completely disappears. It should just like disappear from the night sky. Is that what happens? No? Jesse? The ring is what we see when when the moon covers up the sun because of the solar flares. Like there's a corona around the sun. Here, there's not a solar flare, but there is something that happens. Does anybody know? Does anybody know an alternate name for a lunar eclipse? Some people call it a blood moon. So what happens is the Earth has an atmosphere. And so the same way that, the sky looks blue, it's because, again, of the atmosphere. When you're on the moon, the sky looks black. You don't see anything but the darkness, the emptiness of space. The sun's rays will refract off of our atmosphere, and a very small amount of it will get redshifted and hit the face of the moon and come to us. So what you're about to see, this is the moon beginning. This is a video, again, I stole from YouTube. The moon is right here. It's about to enter totality. So this part is still in the penumbra. This part is in the umbra. And hopefully the resolution will be good enough that what you'll see is once it gets to totality, once the moon is completely inside, it's going to go red. And it's going to be so dim relative to what it previously was that the camera is going to readjust its iris, right? You open up an iris and let more light in. And as a result, the stars that would be behind the moon all of a sudden become visible. Like right now, the moon is so bright that the stars around the moon are not visible. But check out what happens. So here we go. We're entering totality. We're almost there. And now what we're seeing is the blood red moon. And do you see the stars that are moving behind the moon as the moon makes its way, this blood moon makes its way across the umbra? And then here it is starting to come out of totality. And we're getting, and of course, this is sped up. And there's the moon coming out of totality. And now it's back in the, it's still, it's in the, it's still being obstructed somewhat, but it's in the penumbra, which looks almost, it's like 95% as bright as it usually is. Okay, does that make sense? Everybody's clear on what's happening when you're observing this blood moon? Okay, so people observe this phenomena, and it's not until Aristarchus that he put this extra ingredient in. Here's what he says. He says, time, how long it takes from when you first start getting towards, when you first enter the umbra, like when the moon first touches the umbra and a little chunk of it is starting to get cut off, until it starts exiting the umbra. So from this moment or just before this moment, let it go into the umbra and let it stay in the umbra. How do you time? You don't have like a stopwatch. There's no Swiss mechanism for it. Like maybe you drum or something and you know that you're drumming at 60 beats a minute. Here's the moment where you should stop it right there. When you start coming out of the umbra is where you should stop it. And so the amount of time that takes, it turns out, is about 3 hours. Okay, again, this is all very rough estimates. So this is from Aristarchus's document, original document. I mean, not original, this is probably only several hundred years old instead of thousands of years old. So what you measure, you think of the moon starting here. When it just starts to enter totality, this is the umbra. Now, really, the umbra is an entire cone, and I'm just talking about the slice of the umbra through the plane where the moon is traversing it. So you start here, and you're going to move to there. Does everybody see that? That's when we first enter totality to when we first begin to exit totality. And you time that, and that's about 3 hours. The other thing you want to time is when the moon first starts entering totality to when it stops and when it's totally in totality. Let me draw these pictures. So the two things you want to time. Let's go back to blue. Okay, so here's the sun. Here's the Earth. Well, we know now that the Earth is smaller than the sun, but maybe we didn't back then. And the moon is over here, and the moon is going to pass through the umbra. This is the umbra, and then it's going to come back out. So scenario one is you just time how long it takes from this point to this point. And you time that, and that's 3 hours. Scenario two, or calculation two, it's the same scenario, it's the same event. Okay, here we are, same event. But now what you're going to measure is just how long it takes from when it first touches to when it's first inside. That's kind of a bad picture. To when it's first inside. There we go. Okay, so think about the distance that this point travels. What's the distance that this point travels? From here to here. So this took 1 hour. 1 hour corresponds to a distance of, does anybody see what we're measuring? The diameter of the moon, exactly. The diameter of the moon. That's exactly how far we've traveled. We've traveled from one tip of the moon to the other tip. So 1 hour corresponds to the diameter of the moon. What's 3 hours? From here to here, from this point to that point. The diameter of the umbra. Exactly. This is the diameter of the umbra. Does everybody see that? So we know the ratio. So the diameter of the umbra to the diameter of the moon is 3 to 1. Is 3. That ratio is 3. Okay, the diameter, the umbra is 3 times as large as the moon. Everybody see that? Everybody understand that calculation? That little timing calculation? So let's see that again. So what this means is the diameter of the umbra is 3 times the moon's diameter. So then Aristarchus imagines the following setup. Let me do it over here. So we're going to keep the same picture. I'll make the sun a little bit bigger. Here's the sun. Here's the earth. And I don't even need the moon anymore. But I do want the umbra. So over here is the umbra. Right? It's this imaginary plane through which the moon is gonna travel. So there are 2 triangles that Aristarchus considers. This triangle, this is the center of the earth. This triangle and that triangle. What do you notice about these 2 triangles? Say it again. They're not congruent, but they're... Yes, exactly. Their ratios are all the same. They're similar triangles. They're similar triangles, right? Everybody see that? These triangles are similar. Yeah, similar. Yeah, exactly. Equivalent. Yeah, they're similar. Just no, and neither is this one. Maybe this one's poorly drawn. So that's why I tried to mark where the center of the earth is. Here, there's a better picture here. Oh, here. There we go. Okay, so we're going from the umbra to the earth, and then we're going from the earth to the sun, and then just dropping these perpendiculars to those parallel lines. And let's try to unpack what's going on here. So what is this? What is this distance? Where is this umbra? It's where the moon is. So the distance to the umbra is the distance to the moon. Yep, exactly right. That's the distance to the moon. How about this distance? The distance to the sun. Distance to the sun. How about this height? It's the radius of the sun minus the radius of the earth. This is exactly the radius of the sun minus the radius of the earth. Everybody see that? The radius of the sun would be this. We have to subtract off the radius of the earth. Just. This distance is the same as that distance. Let's see if we can see it better in this picture. This distance is the radius of the earth, which is exactly that distance, because these lines are parallel. Yeah, so this triangle is not going to the center of the earth, but this triangle starts from the radius of the earth and goes to the radius of the sun. Does that make sense? How about this little sector here? How can I draw this? Well, I'll just draw it here. How about that? It's the radius of the earth minus, it's not the moon, it's the umbra. It's the umbra. So this is the radius of the earth minus the radius of the umbra. You'll see it clearer here. This is the moon is just somewhere, but the umbra is 3 times the moon, and it's this that we can measure, at least in our minds. So far, so good? Does this make sense? So this is the distance to the moon. This is the distance to the sun. This is the radius of the sun minus the radius of the earth. This is the radius of the earth minus the radius of the umbra. That right there is the radius of the umbra. So far, so good? And if those things are similar triangles, we get an equation that the distance to the moon, so this distance divided by that distance, divided by the distance to the sun, the base is to the base as the height is to the height. The height here is the radius of the earth minus the radius of the umbra, divided by the radius of the sun minus the radius of the Earth. So far, so good? Everybody with me? So that's the calculation that we get out of imagining this heavenly this pair of heavenly triangles. Okay, we're almost there. Distance to the moon divided by the distance of the sun, because of solar eclipses, is the same as the diameter of the moon to the sun, which is the same as the radius of the moon to the radius of the sun. Right? These are all in proportion. So this is the same as the radius of the moon divided by the radius of the sun. So now everything is in terms of radii. The radius of the umbra is what relative to the moon? Three times. Because it takes 3 hours to traverse the umbra and 1 hour to traverse the moon. So this is 3 times the radius of the moon. And now we have an equation that only uses radius of the moon, radius of the sun, and radius of the Earth. Let me just complete this. Radius of the sun minus radius of the Earth. Everybody with me so far? Let's cross multiply these things. So I'll multiply by radius of the sun minus radius of the Earth, and I'll divide by radius of the moon. You want to take a second and make sure you're following along? See what you get on your page? How do we get from here to here? So the distance to the moon versus the diameter of the sun, distance to the sun, there we have solar eclipses. So the ratio of the distance to the diameter is the same, whether it's the moon or the sun, and the same thing for the radius, because radius is just half the diameter. Does that make sense? Everybody with me? Okay, so give me a thumbs up when you've cross multiply, well, not cross multiply, but move this up here and move the radius of the moon down there. Just a little proportionate thinking. We would need book 10, no, 5, 6 of the elements. Does anybody remember what book deals with proportionate thinking? Thankfully, we have algebra. Okay, so this becomes the numerator over here. And I'll keep the same denominator. And this becomes a denominator over here. Did everybody get this? I'm just multiplying both sides by radius of the sun minus radius of the Earth. That multiplies it here and cancels it off there. And then dividing both sides by the radius of the moon, which cancels it here and puts it down. Okay. Radius of the sun divided by radius of the sun. 1 minus radius of the Earth over radius of the sun. What's the radius of the sun in terms of the radius of the moon? How much bigger is the sun than the moon? 400. Remember, that's our 89.86 degrees. We got this was 400 times the radius of the moon. That's just this side. Radius of the Earth divided by radius of the sun, where the radius of the sun is 400 times the radius of the moon. Okay, on the other side, we get radius of the Earth divided by radius of the moon minus, what is this quotient? Radius of the umbra divided by radius of the moon is 3.
I'm sorry, I'm pretty lost.
Sure.
You just point it all again.
Yep. So should I go back up here or where? This one? Oh, the 1 minus. Okay. So here I have radius of the sun divided by radius of the sun. That's 1. And here I have minus radius of the Earth divided by radius of the sun. Maybe I did too many steps at once. This is radius of the Earth divided by radius of the sun, but the radius of the sun is 400 times the radius of the moon. So far, so good? Okay. Well, we can move the 3 to this side. 3 plus 1 is 4. And we can move the 1/400th to the other side. So we get radius of the Earth divided by the radius of the moon times, well, there was a 1, and then plus 1 over 400. Anyway, none of our calculations are nearly this precise, so let's just ignore that 1 over 400. That's not going to change anything. Right? This is like 1 point. Forget about the fact that this is like a rounding error. Everything is very, very rough. What have we just learned? Exactly. The radius of the Earth is 4 times the radius of the moon. The moon is a quarter of the size of the Earth. Alexander.
1 plus comes from if we use the 1 and 3 times 4.
The 1 and the 3 comes over here. And then this comes over there. Let me make sure that doesn't look like a plus sign. So I have a 1 radius of the Earth over radius of the moon, plus another 1 over 400 radius of the Earth over radius of the moon. So you get 1 plus 1 over 400 radius of the Earth over radius of the moon. And the 1 over 400 is a rounding error. So just forget it. So roughly we get this. Wait a second. The moon is how much smaller than the sun? What's the ratio of the size of the moon to the size of the sun? 400 to 1. So if the Earth is 4 times the moon, the sun must be 100 times the Earth. And this is where Aristarchus has a problem. The sun is giant. It's 100 times the Earth. And it's supposed to be governed by the whims of the Earth and not the other way around. So this is exactly what happens. Is everybody okay with this calculation so far? Josie. Oh, the jump from, yeah. So the moon is a quarter of the Earth, and the sun is 400 times. I mean, I can't really draw 400 times. The sun from here to here is a factor of 400. From here to here is a factor of 4. So how much is it from the Earth to the sun? Factor of 100. Okay, you multiply by 4, multiply by 400. So the sun, if you think about the sun, I don't know if I can draw this. Here's the sun. And if you draw 100 Earths, 100 Earths will make their way across the sun. Okay, that's massive, absolutely massive by the definition of mass. Okay, so let's just, this is going to go through that same calculation, but we did it ourselves. So the radius of the Earth is about 4 times the radius of the moon. So far, so good. Okay, so what have we now learned? We've learned that the diameter of the sun, or the radius of the sun is 400 times the size of Earth. And this is where Aristarchus says, hey, maybe heliocentrism is what's going on. Maybe we go around the sun and not the other way around. Yeah, let me hide that for a second. So how come people say Copernicus is the one who predicted heliocentrism? Yes, he's definitely the one who convinced the people around him that that's what was going on. Why wasn't Aristarchus? The Greeks are very sophisticated people, right? They have a deep understanding of all kinds of mathematics, including this heavenly math. Why didn't that convince them? Is it that there's no Catholic Church? It's 300 years before Jesus. So there's no one to, I mean, not that they don't have their own problems, but there's no one sort of, and what Aristarchus is doing is dangerous. He's stealing secrets from the gods, right? Each of these heavenly objects is its own god, and he's like wrestling secrets away from them. This is dangerous stuff. Galileo was, in good company, shall we say, to be getting himself in trouble. It's not that they are, religious fanatics or something. They had a very good reason to oppose Aristarchus's suggestion of heliocentrism. They said, wait a second, if it's really the Earth that's moving, suppose it is the Earth that's moving, then here's the celestial sphere. This is where all the stars lie. We think that there's this sphere. And if the Earth is moving around, you guys know what parallax is? Stick your thumb out, close one eye, now close the other eye. Did your thumb move?
Yeah.
Okay. Looking at from different sources, the background stays put, but the things that are closer to you move. And so they're saying as we move around, we would see the stars changing their position. We would experience parallax. And we don't experience parallax. As the Earth moves on this massive distance around the sun, we would be experiencing parallax, but we don't. The reason that they don't is this is the one place where it'd be good to have some instruments, like telescopes. We do experience parallax. And in fact, that's how we know the distance to the closest stars is through the parallax that we need telescopes to be able to observe. So they were right. They had the right argument. They just didn't have the right data. So they came to the wrong conclusion. But scientifically, everything is perfectly sound. They're like, if heliocentrism was true and the Earth was moving relative to the sun, we would see the stars doing this kind of thing as we change from spring to summer to fall to winter. If we're the ones that are moving, we should be experiencing parallax. We're not. We don't observe it. It is there. We just don't have the instruments yet to observe it. So that's why Aristarchus's attempts at heliocentrism failed, for very good reason. Okay, does that make sense? And by the way, Copernicus mentions Aristarchus in his writing, saying he had this idea later.
Can you explain how you would see parallax in the sky?
Yeah, it's just that the stars are so far, astronomically far away, way more than the planets, the moon, the sun, that in order to observe that action, the fact that as we move, some stars, there are stars that are closer than others. So as we move around, these are on the one atomic unit is the distance to the sun. And as we change our location in the relative to the sun, the stars that are much farther away stay still, whereas the stars that are closer start moving relative to the stars that are farther away. But the amount by which they move cannot be measured with the naked eye. Okay, so this is what I mean by we need better instruments to measure that parallax, but it's there. And the Greeks were right to say, we don't see it, therefore we must not be moving. You know, it's a nice theory, but it doesn't agree with experiment. It's just that their experiment was insufficiently accurate.
Still, basically?
Yeah, that the celestial sphere wasn't, that we are not seeing stars moving relative to each other, except for the planets that we know to have this bizarre behavior. Okay, does that make sense? So this is really crucial. It's not just flat earthers saying, no, we're not moving. There's very good, if you were right, we should be seeing this phenomenon. We're not seeing it. They just couldn't imagine the stars really were as far away as they are. And they said, sorry, we don't buy. Okay. Our final ingredient comes from this guy, Eratosthenes. A Greek friend of mine said, oh, you mean Eratosthenes? So apparently that's how you say it. He actually had a correspondence with Archimedes. And he is the chief librarian. Remember, we talked about this amazing library at Alexandria. He's the chief librarian. He's a poet. He's a music theorist, a geographer. He works in number theory. There's something called the sieve of Eratosthenes. And he provides the final ingredient for what Aristarchus was looking for by measuring the circumference of the Earth. Let's go over quickly how he does that, and you'll see how all of those pieces will finally come together. Aristarchus has set up, we know all of the relative sizes. We know that the Earth is 400 times the moon. We know that that the moon is 1/400th of the sun, that the Earth is 4 times the moon, and we know relative distances between these things, but we don't have any one measurement as an absolute measurement that will cascade to all the others yet. This is where Eratosthenes comes in. So let's talk about how he measures the circumference of the Earth. This is another very important calculation, again, using trigonometry. All of this is about measuring things you can't touch from thought experiments, just from using your head. Okay, so it doesn't really matter that he did know this, that the reason we have seasons is that as we go around the sun, our own orbit around ourselves is not perpendicular to that plane. It's at an angle. And so as we spin, when in the northern hemisphere, when we're closer to the sun, when we're facing the sun and we get more of that direct sunlight, that's called summer. And when we're over here and we get less of that direct sunlight and more of the tangential sunlight, that's winter for us. And of course, it's the opposite in the southern hemisphere. Another reason the Earth can't be flat. Okay, so it doesn't matter that there's this angle, but what does matter is that what they knew, what the ancients knew, is that apparent. I mean, this is all folklore anyway. Apparently, there's a city called Cyan, modern Aswan in Egypt, which is nearly due exactly south from Alexandria, which is where Eratosthenes is. And it's some number of stadia away. We don't really know what a stadium is. In reality, it's roughly 500 miles away. How could you possibly measure 500 miles? Now, 500 miles you can measure. It's a very long distance, but a camel typically walks 10 miles a day, and it's a 50-day camel ride from Alexandria to Cyan. Okay, so there's, if you buy that, then you can imagine measuring that distance is roughly 500 miles. So far, so good. So you know where Alexandria is, you know where Cyan is, it's nearly exactly due south, and that distance is 500 miles. The other thing that he knows is that there's this very, very deep well in Cyan. Hopefully you can see that right there. There's Cyan. There's a very deep well. You usually can't see the bottom of a deep well, but on the summer solstice at high noon, you can look all the way down to the bottom of this deep well. So what that means is, let's think about this. So here we are. Here's the Earth. Here is Cyan. Here is, I'm going to make it much larger than it actually is. Here's Alexandria. And there's a deep well here. And on the summer solstice, at high noon, at the summer solstice, the rays from the sun, which are coming right into Cyan, are going straight to the bottom. Now, the sun is so far away that we can imagine those rays are all parallel by the time they reach Earth. In Alexandria, there's an obelisk, some big, you've seen these big, like Washington Monument looking thing. And at high noon, on the summer solstice, you can measure its shadow. You can measure the shadow that it leaves in Alexandria. And from that shadow, you can determine that shadow, that length tells you this angle alpha. And it turns out that angle, let's say just in terms of not even radian, but just a fraction of a circle, it turns out that it's 1/50th of a circle. In other words, 2 pi over 50. Look. The angle between this, so the sun is over here. The lines are coming out parallel. The rays of sunlight are coming, because the sun is so far away, we can pretend that they're parallel. And at high noon on the summer solstice, Cyan is getting hit, and Cyan is on the Tropic of Capricorn. Capricorn or Cancer? Do I have it here? Is it Cancer? Cancer, yes, Cancer. So Cyan is on the Tropic of Cancer, which means at high noon, that's exactly where the sun's rays are coming straight down onto Cyan. And this angle is 1/50th of a circle, of a full circle.
Like, what's the angle?
So the angle is the angle from straight up out of the Earth, which is what this obelisk is, like the Washington Monument, this big giant thing going straight up. You know it's not the Leaning Tower of Pisa, so you know that it's straight up. And then based on what shadow it leaves, you can work out from this triangle what this angle must have been. I'm glossing over that in the interest of time. Okay, so based on the shadow, you can work out this triangle and work out that angle. That angle is 1/50th of a circle. What does that tell you about this angle? Exactly. This angle is also, as an angle, it's also 1/50th of a circle. It's the same angle. This is also alpha, because these lines are parallel and there's a traversal. Everybody see that? So that's also 1/50th. And that's 1/50th. And this distance is 500 miles. So if that distance is 1/50th of a circle, what is the entire circumference? Exactly. Exactly. So circumference of Earth must be this 500 miles times 50. Because the distance between the angle from the center of the Earth between Alexandria and Cyan is 1/50th of the circle, and that's 500 miles. So to go all the way around, you got to multiply by 50. So that gets us 25,000 miles, which is roughly, to first order correct. Everybody see that? So if that's the circumference, what's the diameter of the Earth? What's the ratio of circumference to diameter? On any circle? Pi. Pi is 3 and a little bit more. 25 divided by 3. 24 divided by 3. Yeah, 8,000. 8,000 miles, which is roughly right. And so what's the diameter of the moon? It's a quarter of the Earth. 2,000 miles. What's the diameter of the sun? It's 100 times the Earth. 800,000 miles. 800,000 miles. What's the distance to the moon? Remember, the ratio of the diameter of the moon to the distance to the moon is this 0.008. That's from the dime. So that's 2 over 250. So 8. No. Redo. Okay, good. So the diameter. Come on. The diameter of the moon to the distance to the moon is this 0.008, which is 8/1000ths. 8/1000ths is 4 500ths, and 4 500ths is 2 250ths. So if the diameter is 2,000 miles, then the distance to the moon is 250. The ratio is 2 to 250. So this is 2, then the other one is 250. So, let's try to make this a slightly easy. Come on, slightly easier computation. So this is 250,000 miles. By the way, the distance to the moon from the Earth is less than half of the diameter of the sun. The diameter of the sun is 800,000 miles. The distance to the moon is only 250,000 miles. Okay, just to put that in perspective. And what's the distance to the sun? It's the same. So this is 8/1000ths. So if the diameter of the sun was 800,000, then the distance to the sun is 1,000 hundred-thousandths. 1,000 hundred-thousandths, also known as 100 million miles. So the sun is about 100 million miles away. And we didn't leave our bedroom to do any of it. Well, okay, we had to walk. We had to know how long a camel takes to walk from Cyan to Alexandria. We had to put a dime on a window. We had to observe the lunar eclipses, the solar eclipses, and time something. The ancients all knew all of this, and they did it with their bare hands, just as you have now done it. How crazy is that? That's trigonometry. That's the power of trigonometry, is understanding all of these things about the gods, about the heavens, without having any access to any fancy equipment. Cool?